Theorem 1 states that M rho is a compact matrix space if and only if every sequence of points in M has a subsequence which converge to a point in M rho. First, we let M is compact in M rho, and we let F is an open set in M. Since M is bounded and closed is in M rho, it has a convergent subsequence which converges to a point in a set M rho because the set itself is closed.
Next, Theorem 2. If A is a closed subset of a compact matrix M rho, then the matrix space A rho is also compact. So to prove that A closed, then A rho is compact. Let's assume X is a matrix space M rho. Let A be closed subspace of compact X, which A is a subset to X. The collection of U alpha is open cover of A since A is closed. The collection of U alpha is union to A complement which contain finite sum that contain subcover which is X is compact. Therefore, the collection of alpha 1 until alpha n such that the collection of alpha U alpha n equal to 1 until capital N is union to A complement that cover X. Hence, U alpha n that n equal to 1 until capital N must cover A. Thus, A is compact and matrix space A rho is also compact. Okay. Next for Theorem 3, let A be a subset of a matrix space M rho if A rho is a compact space, then A is closed subset of M. So to prove that, let Xn be a Cauchy sequence in A rho, which converge to the point X in element of M. So X is a limit point of A. Since A is a compact, then A is a complete. Since A is a complete, every Cauchy sequence in A converge to a point in A. Thus, Xn converge to the limit point X in element of A. Thus, A contain all its limit point. For example, A equal to A bar. So, hence A is a closed.
Okay, next for Theorem 4. The theorem says if M rho is a compact matrix space, then M rho possesses the Heim-Borel characteristic. From the theorem, it says M rho is a compact matrix space. Compact matrix space is satisfied to bounded and complete entirely. So, for bounded entirely, we let closed interval A to be element of M. There exists finite number of covers. We let A1, A2 until AK covering M. So this is the notation which is K1 until N. N is a sum that finite number. So for the Heim-Borel characteristic, we let finite set equals to G1, G2 until Gk there exists element of A. G1, G2 until Gk is element of A. A is open cover of M, which is also G1, G2 until Gk is covering M, which this is the Heim-Borel characteristic, which also same with bounded entirely, which is the set is covering M. Next, for theorem 5, it say if M rho possesses the Heim-Borel characteristic, then M rho is a compact metric space. By the definition of Heim-Borel characteristic, for all open cover of finite closed interval A to B contain finite open subcover. We can prove by for all open cover of open interval A to B is not element of finite open subcover. To show that G is not element of finite subcover, we let G open interval A1 to B1, open interval A2 to B2 until open interval AM to BM. So we assume that epsilon equals to minimum of A1, A2 until AM. Then epsilon is greater than 0. Then finite union of set G is open interval A1, B1 union to A2, B2 and so on until open interval AM to BM. And this is a subset of open interval epsilon to 1. So we have open interval 0 epsilon closed interval and open interval epsilon 1 open interval is disjoint and not cover of A. So we can conclude here the closed interval of AB is the element of finite open subcover. We can say compact when it has finite subcover.